All right, our next major unit is waves, and we'll start that conversation with something called vibrations. So, a vibration, we'll go through all of these key terms as we move through today's lesson. So, we have the word vibration, we have medium, we have mechanical wave, we have elastic, and we'll talk about wave speed and distance a bit and composition of the medium and how those all play a part in vibrations and waves and those types of things. So vibrations in mechanical waves. So the cyclical motion about an equilibrium point is called a vibration. Okay, so if this was my let's see, if this is my equilibrium point, if I was to graph or draw a picture of something going back and forth, it might be doing something like this. This is a vibration. Okay, if you've seen a heartbeat, it looks something like this. Okay, those are types of vibrations. We'll talk about waves. They can be really pretty, they can have symmetry and things, they can also be very erratic. Okay, so the transfer of energy through a material by particle vibration is called a mechanical wave. Okay, so here's the key piece. For a mechanical wave, we need to have particles. Okay, so you'll hear about X-rays and and the electromagnetic waves and those types of things, but we're going to be dealing with particles. So we're going to have medium, which is a stuff or a substance that we can actually transfer our mechanical wave through. Okay, so you're going to hear the term wave. It's going to extend to other topics, but for what we're looking at right now, this will be a mechanical wave. It needs a medium, which means it needs stuff to travel through, and that stuff can be a solid, a liquid, or a gas. Okay, so when vibrating, the medium tends to gain or lose very little energy. Okay, of course, everything loses a little bit of energy through movement and friction and all those types of things. But when we're talking about mechanical waves, they are incredibly efficient. Okay, so we'll be modeling a lot of the ideal situations here, but we'll be looking at very efficient, not quite lossless, but almost lossless waves in most of our conversations. Okay, so it's one of the most efficient forms of energy transmission in nature. We do have to be a little bit careful when we model waves like the picture down below here. Okay, what we tend to sometimes think of as waves are the waves we see close to shore, and those waves sometimes look like this. And they are waves, but if you look another 10, 15, 20 feet out, those are probably waves that are better representations of what we're going to talk about. Okay, so the net motion is something we're going to talk about. So net motion is the displacement of a particle over a certain time interval. So if you were to look at the full cycle of a particle, what you'll notice is that normally, and you can see this in deeper water when waves are a little farther off from shore, if you had a bobber, like a fishing bobber or something in there, the object or the bobber will go up. It might move forward a little bit, but then it goes down and then it goes backwards a little bit, and you'll find that the particle generally moves in little circles. Okay, so waves we tend to think of like this blue one I've drawn here close to shore where the water's thrown up onto the shore. But most waves that we're talking about, especially in water waves, particles just go in little circles. Okay, so this little dude here, he would just kind of go in a little circle. Okay, if we were watching that. Unless it gets close to shore and then things change a bit. Okay, so if the net motion of a particle for these mechanical waves is zero, essentially zero, if it just goes in a little circle, so it comes back to where it starts, then if you think of our work equation with force times displacement, if the displacement's zero, then no work is done. So by returning to the original location, we've essentially stated that there's no energy loss. Okay, so that's a really big idea for what we're going to talk about today. Some keywords. Okay, so vibration, the cyclical motion of an object about an equilibrium. Okay, so you could take some spoons and knock them together. You could see a flag fluttering in the wind, a guitar string, a tuning fork. There's lots of different options you can see to see a vibration. Okay, mechanical wave is the transfer of energy through a material due to a vibration. Okay, a medium is the material that permits the transmission of energy through vibrations. And net motion, the displacement of a particle over a certain time interval, the difference between the particle's initial and final positions. Okay, so those are just keywords. You can pause it here, jot them down, put them wherever you want. This is a fun little video. If you're a musician or any kind of drummer, this is fun to watch because they do a really high-speed filming of a drum kit and specifically a cymbal, and you will be amazed at what happens to a cymbal when you hit it with a drumstick. Okay, so lots of words here. Again, you can pause these and read them at your leisure. I'm just going to highlight some of the key points. So particle behavior in different media. So vibrations need a medium to transfer waves. So that's our first key piece. Okay, so one of the mediums we'll start talking about is a solid medium. So we have atoms that are held really close together in some sort of crystalline structure inside. That's what makes up a solid. Okay, and these forces are pretty strong. So when you displace or move them, they want to return back to where they started. Okay, and we generally call this elastic. Okay, you can have inelastic, where if you deform an object, it doesn't go back to its original starting location. If you think of a pink eraser, you can bend it quite far, but if you release it, it will eventually just go back to the way it started. If you bend it too far, it will tear, and then you've moved into an inelastic zone where you've done permanent deformation. Okay, so rigid materials transfer mechanical waves much more efficiently than less rigid. Okay, that's a really big idea, and we'll do a little test near the bottom here that you can do at home while you watch this. So the less rigid a medium, the less efficient it is at transferring a vibration. Okay, so these are big ideas that are going to sort of filter into our conversations and some of our questions that we're going to work on. So key piece down here, right here. Okay, the speed and distance that a wave can travel, okay, are affected by this efficiency and how rigid a material is. So the speed and distance that a wave can travel, those things are affected by the medium that you work with. So if you want to do a little test, and I love doing this one in class, so you're just going to have to try it at home though. If you take a coin or a pencil or even your fingernail and just scratch the table a little bit that you're sitting at, okay, and if you shouldn't be able to hear it, but if you put your ear on the table and you continue to scratch it, you'll notice something really amazing. It's really, really loud. Okay, and you can do this across a room. If you have a long enough counter in your kitchen, you can go and try it. Just be really careful. If you do put your ear on a desk and someone slaps it really hard, it is incredibly loud on your ear. So please, please be careful on that. But it's a fun little test and you can do it at home. It takes 2 seconds. Okay, so liquids and gases are also a type of medium we can talk about. They're considered fluids. Okay, because they have intermolecular contact, not quite as rigid as a solid, but they still have contact between those molecules. They're still very effective at transmitting sound and other types of waves. And we're going to spend a lot more time talking about sound as we move forward. But just as an example, in water, sound travels 5 times as fast and much further in water than in air. And that makes sense. If you've ever tried this and been in a pool or the lake and someone's close by and you yell at them, you can hear it. It sounds different. But if you think bigger and you think of things like whales and dolphins, they use echolocation where they're creating higher sounds than we can hear. And they're using that to locate things like fish or other dolphins, those types of things. Okay, so sound or these types of waves can travel 5 times as fast or and much further in water than in air. Okay, and when we're talking about gases, gases cannot travel. We're going to talk about 2 different types of waves very shortly, but basically the particles have to bounce together in what we call translational molecular motion. That's a tough one. Okay, and that's they're bouncing together to move the energy or the wave through the medium. Okay, there's a nice little video down here if you want to watch. It's a Mythbusters. People like those ones quite a bit. It's a bunker bomb. It's a little history connection with Nazi Germany, I believe. And yeah, take a little look. It's got a neat little water table demonstration. Okay, now mechanical waves, there are two types of mechanical waves that we're going to talk about. So there's transverse and there are longitudinal. So transverse waves, I'll show you pictures in a minute, they're going to go up and down, and longitudinal waves move left to right. Okay, so something like this, a transverse wave, sometimes called a shear wave. A transverse wave describes a wave in which the particles vibrate perpendicular to the direction of flow of energy. Okay, so if energy is going this way, then those particles just vibrate up and down. Okay, and in a full cycle, okay, the particle would move up to the top, move down to the bottom, and return back to where it started. And that's where that net displacement, that net motion of zero comes from. Okay, so guitar strings, some water waves are examples of these. Longitudinal waves. Now, longitudinal waves are waves that, if this is my axis right here, the waves move back and forth this way. Okay, so I'll model these with a slinky in a minute, and I'll give you a bit more of a visual on what's happening. So if you push a slinky, if you compress it all together, you can see this zone right here is all compressed. Oops, better try that again here. This zone right in the middle here is a compression. Okay, and this is going to be, we're going to give this a name in a minute where it's not compressed. So I'm going to do a little video here in a second, and you can see how a slinky behaves in both transverse and longitudinal waves.
Okay, so this is a slinky. It's going to be the medium. So we're going to look at a vibration as any kind of disturbance. Okay, and they can take on different forms. They can be big, they can be small, they can be really, really quick, or really, really slow. Okay, so that's a vibration. We want to focus on the two different types of waves. The transverse wave looks something like that. It can look something like that. We'll talk about that more in the future. Okay, and a longitudinal wave looks like that. Okay, so now there's a piece of tape here you can see, and you can mark it with the floor. As I move it back and forth for a transverse wave, that piece of tape goes back and forth, from left to right, if you will, but it doesn't go down the wave. Okay, and that's sometimes where people think waves are going to carry everything forward. A longitudinal wave, you can see it does move forward, but then it comes backwards and it returns to its starting location. And that's that idea of net displacement. Okay, so quick summary: transverse, longitudinal, any kind of disturbance is a vibration. The slinky's the medium.
Okay, so to give a name to those in the slinky, when we compressed it, they do have a specific name that we do need to know, and that is a compression, which makes sense because we've squashed that slinky together. But this is a weird one. It's called a rarefaction. Okay, so now that's a place where it's actually stretched out. Okay, so a rarefaction is where our pressure is lower, or our density of the slinky is lower, and a compression is where we have higher pressure, or the density of the slinky is all packed together. Okay, and so as those travel, that's where we get our wave from. So we have higher pressure to lower pressure. Okay, so now I also have a couple more fun videos here. There's not a lot of calculation, as you can probably tell so far in this particular lesson, but there are some neat connections. This is a really interesting one. If you watch the edge of the bomb blast, you'll see how the compression has packed the air particles so tight together that they bend light. So as light travels through them, it's actually denser air, and it tends to bend the light around it, and you'll see a disturbance in that particular realm of the blast. Same thing with the sonic boom. Really interesting to watch. So just take 2 seconds and watch those. They're really good. Okay, now sound. We're going to spend a lot of time talking about sound and how your ears work and those types of things, but sound is a longitudinal wave. It has to travel in air or water or some other medium. Okay, we are going to talk about the range that humans can hear. And you can transmit sound through liquids and solids, okay, but we're more used to dealing with the air model. Okay, and we'll talk about all those little pieces. And let's go down here. And then we'll wrap up with A couple little questions. So this is section 8.2. So if we want to look at 2, 3, 4, and then in section 1, I didn't post the picture here, but section 1, 8.1, number 3. Thanks for tuning in.